Look at the chemical formula C6H14. It tells us exactly what atoms are in the system: 6 carbons and 14 hydrogens. That gives the molecule an atomic mass of 86.2, a strict, unchanging baseline. But that simple alphanumeric string is deceptive. The exact same collection of atoms can morph into completely different physical architectures, known as structural isomers. This diagram shows the topological expansion of C6H14. Starting with a straight carbon chain, it rearranges into 5 distinct structures: N-hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane. As the chain branches, quantitative labels show the boiling point dropping sequentially from 69 degrees down to 49 degrees. The exact same collection of atoms, with the exact same mass, produces completely different physical realities based solely on internal topography. There is a similar contradiction in their chemistry. Alkanes are notoriously inert. They lack reactive functional groups. Yet, under the right conditions, we can force them to undergo violent chemical transformations. To break that chemical inertness, we have to bombard the molecules with high-energy ultraviolet light, triggering a cascade known as a radical chain reaction. Mastering a hydrocarbon requires looking past the static formula on the page. We have to map its 3-dimensional topography and locate its hidden thermodynamic vulnerabilities. Constitutional isomers are molecules that share an identical formula but have entirely different atomic connectivity. We can systematically map every constitutional isomer of C6H14 using a chop and branch method. We start with the baseline 6-carbon straight chain, N-hexane. By severing the terminal carbon, we are left with a 5-carbon pentane chain and a free methyl group. Attaching that severed methyl group to the second carbon of our new chain creates our first branched isomer, 2-methylpentane. Shifting that methyl group one position over to the center carbon creates a distinctly different architecture, 3-methylpentane. These are distinct chemical entities, proven by the specific proton environments in their proton NMR spectra. The unique symmetry of 2-methylpentane produces a peak ratio of 6:1 to 2 to 2 to 3, whereas 3-methylpentane yields a distinct 6:4 to 1 to 3 ratio. To find the remaining isomers, we continue the derivation by severing another carbon from the chain. This leaves us with a 4-carbon butane base and 2 free methyl groups to place. In this diagram, you can see the 4-carbon butane chain. Stacking both of those free methyl groups onto the exact same second carbon builds the highly branched 2,2-dimethylbutane. Alternatively, separating those methyl groups onto adjacent central carbons gives us 2,3-dimethylbutane. This structure is highly symmetrical, confirmed by the simple 6:1 NMR ratio appearing below it. It is important to note the strict boundaries here. These are exclusively chain isomers. Because they lack chiral centers or restricted double bonds, they do not exhibit any form of stereoisomerism. This systematic derivation shows relying on a molecular formula alone fails to capture the physical reality of the molecule. True chemical intuition requires spatial mapping. This diagram contrasts the thermodynamic extremes of our derived isomers. We have N-hexane boiling at 69 degrees, side by side with 2,2-dimethylbutane boiling at 49 degrees. Each is enveloped by a translucent boundary representing its total outer surface area. The elongated, linear shape of N-hexane gives it a high surface area. This geometry allows multiple molecules to stack tightly together like bricks, creating broad, flush contact zones along their entire lengths. Maximizing that surface contact directly strengthens the London dispersion forces between the molecules. Stronger intermolecular forces require a higher input of thermal energy to break, driving the boiling point up. Conversely, the extreme branching of 2,2-dimethylbutane forces the molecule into a compact spherical shape. When these branched structures attempt to stack, their boundaries clash. This steric hindrance leaves only minimal, pinpoint surface contact between the molecules. The resulting drop in dispersion forces is what pulls the boiling point down to 49 degrees. Topological branching directly dictates molecular packing efficiency. The spatial geometry of a hydrocarbon is the true governor of its physical phase. Regardless of their physical shape, all alkanes share a profound chemical inertness. This diagram isolates the fundamental building blocks of the molecule, the carbon-hydrogen and carbon-carbon single bonds. Looking at the electronegativity values displayed here, we see numerical parity. Because carbon and hydrogen have very similar electronegativities, they share their bonding electrons evenly. There are no regions of partial positive or partial negative charge anywhere on the structure. Without those dipoles, the molecule is completely invisible to standard electrophilic or nucleophilic attacks. There is simply no charge gradient to invite a reaction. The second barrier to reactivity is that these bonds are massively strong. The bond enthalpy values shown here dictate that breaking a carbon-carbon bond requires 348 kilojoules per mole, and a carbon-hydrogen bond demands 414. Cleaving these stable sigma bonds requires a massive, targeted input of energy. This creates the kinetic stability paradox. Alkanes hold vast amounts of stored energy, which is why they are highly combustible and thermodynamically unstable, but structurally that energy is locked away behind a formidable kinetic barrier. Without a specialized mechanism capable of bypassing strong, non-polar bonds, an alkane remains functionally dead to organic synthesis. The solution to this kinetic paradox is the free radical substitution mechanism. To bypass the high bond enthalpies of the alkane, we need a specific environmental trigger: high-energy ultraviolet light. This diagram illustrates step 1, initiation. A diatomic chlorine molecule is struck by a UV wave. The energy causes homolytic fission, cleaving the bond in half. Single electron arrows show one electron moving to each chlorine atom, generating two highly reactive chlorine-free radicals. This initiation step is strictly endothermic. It is the only way to force the creation of the vital, electron-hungry radical needed to crack the alkane. In step 2, propagation, the aggressive chlorine radical attacks the stable alkane, abstracting a hydrogen atom. This forms hydrochloric acid as a byproduct and leaves behind a methyl radical. That specific abstraction transfers the radical instability directly onto the carbon skeleton. The previously inert alkane has been turned into a highly reactive intermediate. This new alkyl radical immediately attacks a fresh chlorine starting molecule. It strips away one chlorine atom to form our final alkyl halide product, chloromethane, and crucially regenerates a new chlorine-free radical. Because a new chlorine radical is generated in this step, the reaction becomes a self-sustaining continuous loop. One initial burst of UV light can functionalize thousands of molecules. The process finally ends in step 3, termination. The chain reaction dies when any two free radicals happen to collide with each other. They form a new stable bond, consume the free electrons, and halt the propagation cycle. Alkanes are not truly inert. Their kinetic barrier is steep, but homolytic fission provides the reactive intermediates necessary to initiate functionalization. The breakdown of C6H14 reveals the dual nature of the alkane molecule. Physically, the carbon skeleton is modular. We can manipulate it through chain branching to intentionally tune the molecular packing and volatility of the substance. Chemically, homolytic cleavage allows us to strip away the inherent inertness of these nonpolar bonds, converting stable structural skeletons into reactive building blocks. However, there is a primary practical limitation to radical halogenation. Because free radicals are so violently reactive, they attack the carbon chain indiscriminately. The result is rarely a single pure product. It is usually a messy mixture of heavily substituted byproducts. To impose order on that unpredictability, organic chemists must rely heavily on precise stoichiometric ratios of the reactant gases and leverage the specific spatial topography of the isomer to control where the radical strikes. True mastery of organic chemistry means seeing beyond the simple formulas written on the page. It requires mapping the three-dimensional architecture of the molecule and understanding the precise thermodynamic triggers that govern how these molecules bond and react.